things, new habits, new routines. Humans don't like change, typically, until they get used to it, and then they're fine, right? Connor, can you get used to this? It's November, you guys. It's November out there. Are you a snowmobiler? You like snow. Do you, what's that? Do you like snow like still in April like last year, or no? Are you over it by then? You still like it? Wow. I've got an idea for you. Alaska. All right. That's true. No daylight is no good. I know. Yeah. Yeah. I'm with you. All right. Oh, what is a radian? It's not a degree. If I asked you how big 1 radian is, could you tell me? Yes, that is more of how you convert, though. If you're really backing up and thinking, like, what is a radian? What defines 1 radian? If you are looking at a random angle, okay, the measure of that in radians comes from the SOR formula. Do you remember that? Yes? And radians is your theta, so I'm going to solve for that. The number of radians that an angle is a ratio of S to R. Do you remember what S was? Anybody remember what S stood for in the SOR formula? The arc length. Good. And R, don't disappoint me. Thank you. So if you have a random angle and you have your arc length, like as if this was kind of opening up like a ray does around a unit circle, it's a ratio of your arc length to your radius. So right now, does this look shorter, longer, or the same as the length of my R? Just roughly speaking, do you think it looks smaller, bigger, or the same? Slightly smaller, I think so. And so if it's slightly smaller on the numerator than on the denominator, what's that value going to be of that number? Slightly under 1. So this is probably slightly less than 1 radian. Okay? As soon as you open up, if we keep opening this angle, as soon as it gets to, the radius is the same length the whole way, right? The arc length, though, is going to grow. If I were to do that and let it grow just a little bit more, so we'll call that S1, and we'll call this bigger one S2. Now let's pretend those are the same. As soon as it becomes the same arc length as it is the size of the radius, now we've accomplished 1 radian. Yes? Which happens to occur at around 57 degrees. Okay? Which is what 180 divided by 3.14-ish would be. Right? 180 divided by pi. When it opens up, there's your radius. When it opens up such that your arc length is twice the size of your radius, then that ratio becomes 2 to 1, and that would be approximately 2 radians, which is approximately 114, 115 degrees. Okay? And then if you open it up in a full circle, what is the length of your arc length? How big is the full length around a full circle? If I ask you for the distance around a circle, in other words, I'm asking you for the circumference, 2 pi r would be the arc length in that case over r, which is why 360 degrees, a full circle, is the same as 2 pi radians. You follow? Okey-doke. So, that's what a radian is. So if you want at the top, 1 radian is approximately 57-ish degrees. And then this first example is going to make us make use of that SOAR formula. So a central angle theta in a circle of radius 6. So they're giving us our radius of 6. Intercepts an arc of length 15. They want to know what's the radian measure. By the way, do you remember that the SOAR formula only works with radians? If you plug it like 30 degrees into it, you're going to get it wrong. Okay? So divide both sides by 6, and theta equals 2.5 radians. So convert each angle in degrees to radians. So these are currently in degrees. I should have put degree symbols. Do you remember that one transformation is multiplying by pi over 180 and the other one's multiplying by 180 over pi? Right? The reason you're multiplying by 180 degrees over pi radians is because that's multiplying by something over itself, right? 180 degrees is the same thing as pi radians. And when you multiply by something over itself, you're multiplying by 1 technically. Agreed? You're changing the appearance, but you're not changing the value because you're multiplying by something over itself. So if and when you get confused as to whether or not to multiply by 180 over pi or pi over 180, does anybody have a good way of remembering? That does not categorize as memorizing it. Anybody? Olivia? Very good. If you're going from radians to degrees, the radians, which already have a pi, usually, in the numerator would need the pi in the denominator. And you can think the same thing with degrees. If you want the degrees to cancel out, this degree symbol's in the numerator, so you'd multiply by pi over 180 degrees, so the degree in the denominator and the degree in the numerator would cancel. So this one is where we multiply by pi over 180. Your degrees cancel. Those zeros will cancel. 3 over 18 is 1 over 6, so this is just pi over 6. And you should remember that from last year. Pi over 6 is 30 degrees. Yes? Do you remember, without doing it, what 90 degrees was? Pi over 2. We can obviously do that out. So your zeros will cancel. 9 over 18 is 1 over 2. Now, negative 135 is not one of your reference angles, so you probably don't remember that. But do you remember what the reference angle of 135 is? Or negative 135, doesn't matter if it's the same reference angle. Anybody remember the reference angle of 135? No? Do you remember how to find reference angles? Oh boy, Mrs. Rahill's got her work cut out for her. Joe, save me. Right. However many degrees it is shy of or past 180, right? or 0 or the x-axis, period. So this would be a reference angle of 45 degrees. Does anybody remember what 45 degrees is in radians? Pi over what? Good, Andrew. Pi over 4. But it's not necessarily going to be a plain pi over 4 here because this isn't a 45 degree angle to begin with. It just has a reference angle. So it might be 3 pi over 4. It might be 5 pi over 4. Do you follow? But it's something pi over 4 because the pi's over 4 go along with 45 degree reference angles. So if I multiply this by pi over 180, my degrees cancel. 135 and 180 are both divisible by 5 or 15. Well, let's reduce it by 5 first. So 135 divided by 5 is 1027. And 180 divided by 5 is 20, 30, 36. Did I do that right? Sorry. Pushing in on mental math here. 5 goes into 150 30 times with 30 degrees left over, and 5 goes into 36 more times. Okay. Now these two, it is reducible by more. What goes into 27 and 36? 9. So negative 3 pi over 4. So if 5 went in and 9 went in, what could I have taken out right from the start? Andrew? 45. I just didn't realize it. Now I see it. Whoops. It's November. It's coming for you. All right. Next exercise. So, by the way, that over 4 came to light, as we thought. Convert each angle to radians. So pi over 3, when you're over 3, do you remember what the reference angles are that always correlate with being over 3? 60. So it might, it's going to be some degree measurement that has a reference of 60 if the denominator is 3. This particular one, which is actually, it is the reference angle of pi over 3. If we multiply by 180 over pi, pi's cancel, as Olivia says. 180 divided by 3 is 60 degrees. So this one, which also has a denominator of 3, whatever the degree measurement that I get, should also have a reference of 60. But this one takes a little bit more work to figure out exactly what that degree measurement is because it's not going to be 60 verbatim. Multiply by 180 over pi. My pi's cancel. 180 over 3 becomes 60. 60 times 5 is 300, so negative 300. Can we all agree that negative 300 has a reference angle of 60? And then the next one's a little bit trickier because we don't have a pi in it already, but this is 1 radian. So we still multiply by 180 degrees over pi radians. And you would need a calculator for that. 180 divided by 3.14 gives us 57-ish. And I already told you that 1 radian was approximately 57 degrees, right? 180 divided by pi. Oh boy. Oh my gosh. 57.29577. We'll do 57.3. Okay. Drawing angles in standard position. So, pi over 4. So if 180 degrees is how much in radians? Pi. So essentially what we're doing here is we're splitting that half circle into fourths. Here's pi over 4, which is what they asked for. But I'm going to do more with you here. Here's the second pi over 4. Here's the third pi over 4, and here's 4 pi over 4. Everybody see that? Two of those fractions would reduce to something else. Obviously, 2 pi over 4 would become pi over 2, and 4 pi over 4 is just pi. But I think it's nice to show you that those are like the tick marks separating this half circle into 4. So 1 pi over 4, 2 pi over 4, 3 pi over 4, and 4 pi over 4. Do you follow? Okay. B is turning this, or is splitting the pi up into thirds. So here's your first third, here's your second third, and here's your third third. So this is 1 pi over 3, this is 2 pi over 3, and this is 3 pi over 3. It's like splitting 180 degrees up into thirds. 60 degrees, 60 degrees, and 60 degrees. Yes? This one is splitting it up into 6. So that would be, here's 1/6, here's 2/6, here's 3/6, so 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, and 6 pi over 6. Have you ever seen it done this way? Maybe, maybe not. Of those, 2 pi over 6 obviously reduces to something else, and that's why it coincides with pi over 3. 3 pi over 6 reduces to pi over 2, and that corresponds with pi over 2 and 2 pi over 4. 4 pi over 6 obviously reduces to a 2 pi over 3. 5 pi over 6 is what it is, and then 6 pi over 6. What do you notice about your x-axis, the way I'm labeling it each time? 4 pi over 4, 3 pi over 3, 6 pi over 6. It's always whatever the denominator is, right? Pi over itself. And so on the last one, we're splitting this just up into half. So here's 1 pi over 2, and here's 2 pi over 2. And so what would this be? 3 pi over 2, 4 pi over 2, 5 pi over 2, 6 pi over 2, 7 pi over 2 would be right there. So if I'm actually drawing that angle, just to follow the directions, I went around a full circle and then some. You kind of show your angle of rotation with that. Okie doke. We already talked about our SOAR formula. Do you remember coterminals? Like we just did one. 7 pi over 2 has a terminal ray right here. That's a coterminal to 3 pi over 2, right? Anything that has a terminal ray in the same spot are called coterminals. If you're dealing with degrees, you add or subtract multiples of 360 because you just kind of swing your radius around another full circle. If you're doing it with pi's, what's a full circle in terms of pi? 2 pi. So if it was a pi over 6 term, if you want to make your life easier, you would add or subtract 12 pi over 6. If it's a pi over 12 term, you add or subtract 24 pi over 12. And if it's another pi over 6 term, 12 pi over 6. Just to get that common denominator out of the way. Okay? We will save this linear speed and angular speed until Monday, Tuesday. So the 1 or 2 questions that are on linear speed versus angular speed, just hold off on those. So I'm not sure what exact numbers it is, but if you get to linear speed and angular speed, definitely skip that because that's really the only new concept for you.